One of the interesting things I love about the garden is that people often say that a garden is colorful. And, certainly I feel like our garden is fairly colorful. The peonies are coming up, and the mountain laurel is just opening, and the dogwood is flowering. But if you looked at the whole scene and you carved up how much of it was actually color, that is not just, the general palette green background, it would be like a tiny little fraction of the whole visual field. And so somehow these things occupy much more space in our mind because, probably I would say, because color is really important. I like to say that, paraphrasing Marvin Minsky, it's the things that our visual systems do or our minds do most well that we take most for granted and that probably require the most amount of computation. The fact that you can think of it like that tells you that there must be a lot of brain dedicated to it. I remember recording for the first time, this neuron and it not responding to anything, and then moving my bar of light around and getting some faint response out of the cell, and then changing the color and it responded to purple, a kind of dark purple, nothing else. And I was like, wow. And the next cell that I recorded right next to it responded to a kind of blue. And the next cell I recorded, they just were all incredibly narrowly tuned to specific hues. I was like, this is incredible. I found this sequential shift of color tuning where you got cells that started out, the cells were tuned to red, and they sat physically next to cells tuned to kind of orange, next to cells tuned to kind of yellow. And it mapped out these little color maps, these little chromatopic maps. So this is a drawing that was made during an experiment to document the response properties of a neuron that David Hubel and Torsten Wiesel were recording in primary visual cortex of a monkey. And it turns out that this is probably the first evidence we have for a spatial color contrast calculation in the nervous system. And so you can see this would have been the little patch of the screen that through which light, when it passed over that part of the screen, caused the cell to fire action potentials. And then they used this kind of Baroque code where a red X equals blue on. So wherever the cell responded when you had blue light, that's the red X's. You can see it covers the entire extent here. So wherever blue light was throughout the entire patch there, that caused the cell to fire action potentials. But then it shows this interesting asymmetry where red light shone where there's a little triangle that caused the cell to shut up, to be inhibited, and red light where there's these X's caused it to be excited. So for us, this contrast of the response is a spatial opponent response where red is causing an opposite response in the center and the surround. That's the first indication of color contrast anywhere in the nervous system. And it was recorded by David Hubel and Torsten Wiesel in 1962. And a finished figure never made it into a paper because they didn't get enough evidence to really convince themselves. And it's actually only ever referenced as one line in a paper that was published in 1968. But when I joined the lab with Margaret Livingstone and David Hubel, David suggested that I work on this as a problem to actually figure out whether or not these cells were capable of supporting color contrast calculations. How does the visual system go from what is essentially a line in the electromagnetic spectrum, that goes from red, orange, yellow, green, blue, indigo, violet, where violet isn't really purple, it's just very dark blue with a kind of reddish hint. How do we go from that into what every psychologist will tell you is a circular space that goes red, orange, yellow, green, blue, indigo, purple, and so on back to red all the way around? How do we do that? Well, the brain is a two-dimensional cortical sheet, and in order to process that electromagnetic energy, you need to map that thing onto this two-dimensional structure, which will require that you have to close those loops. And it's in the closing of the loops that you then put next to each other red and blue, which predicts the emergence of what is a cortical color. It's a product entirely of your brain, of purple. Why is it then that we're protected from all of this processing? Like, why aren't you aware of how sophisticated color is? And I think that's the same reason why, the makers of the iPhone, there are no buttons, it looks sleek, and there's nothing in it. I mean, it's like, how does it work? It's magic. Because if there were lots of buttons, if you were aware of all of the sophisticated engineering in it, that would actually get in the way of you using the device. And so evolution has worked hard to protect us from any awareness of how this thing works. So I think, the short answer is we don't have the imagination to be able to understand what the brain is doing. That's why you have to run experiments, and that's where the fun is.